I hope. And I'm going to maximize them. I just need to get you out of my way live. You're exactly where the view button is. Okay. Okay, live. Let me know when you're ready.
Oh, I'm ready. Please, Andreas Kyprianou from the University of Bath. Thank you very much for talking.
Okay, thank you. Thank you very much for the invitation, live. I should say this is the largest audience I've ever spoken to, and also the largest audience that I can't see. I hope you're all well, and I hope you're all keeping well, and certainly keeping your distance from those around you, as we are. So I'm going to talk today about entrance and exit at infinity for stable jump diffusions. Actually, this is joint work with Leif Döring, hence why I'm in communication with him on Sunday afternoons. So I just want to start by reminding you a little bit of history. So back in the 1950s, William Feller classified boundaries for one-dimensional diffusions that live on AB, on the interval AB in one dimension, of course, and A can be minus infinity and B can be plus infinity. And just, you know, I mean, there are subcategories, but the four main categories were regular, if it's both accessible and enterable, so that means you can get there and you can come out of that boundary. Exit if it's accessible but not enterable, so that means you can get there, but you can't come out of that boundary. Entrance if you can come in, but you can't get to that boundary, and natural if neither. So Feller's analysis was largely based around the generator of the one-dimensional diffusing using Hillier-Seeder theory. And actually his first trick was to get rid of the drift term. So you can see, I hope you can see my mouse circling around this term here. This term here can be got rid of by changing using the scale function, so changing scale if you like. So there's a natural harmonic function associated with this operator, and you load up the diffusion into that harmonic function, you get a local martingale, whoops. And so one can also check that under that transformation, the boundaries transform also to another A and another B. So we're still asking the same question for this SDE, but now on a different interval. So it suffices to look at this simple SDE here. And the interesting cases, or not necessarily the only interesting cases, but interesting cases are when A is minus infinity and B is plus infinity. And actually, for us in a bit, it will be when A and B are both minus infinity and plus infinity. And so what we're interested in is entrance at these boundary points. So suppose we set B to be plus infinity and A to be -3, for example. We want to know if we can enter from plus infinity, from the boundary plus infinity, and that's what we're calling it. It has been increasingly commonly been called coming down from infinity. So Feller resolved this issue with his analysis, and he showed that plus infinity is an entrance boundary if and only if this integral test holds. And you can, just to remind you, sigma appeared here, and this would be the new sigma here in this SDE. So the sigma you see here would be the sigma tilde you saw on the previous SDE. So sigma is growing slightly more than linearly at infinity. Okay, so this notion of coming down from infinity, as I said, it's more common to call it that way recently, and this is because we see it appearing in other types of stochastic processes, and also differently from the Feller situation, stochastic processes which undergo jumps, so with path discontinuities. So here's another classic example, the famous one. So this is Kingman's coalescent, which I trust most of the people in the Zoom room know about. So this is simply a model for merging blocks, or equivalently for genealogical evolution backwards in time, if you look backwards in time. So blocks merge at a constant rate. So any two blocks merge at a constant rate. So if you have n blocks, they merge at rate n choose 2, and or n choose 2 times the constant rate that any two blocks will merge. So you can think of the number of blocks as a Markov chain, a death chain. And a natural question here is, can I start with an infinite number of blocks? And that's the question about coming down from infinity, a Markov chain entering at plus infinity. So you're extending the state space of the Markov chain on the natural numbers to include the boundary point plus infinity. Here's another WYSI example. So this is some work I did recently with student Stephen Paget, Chris Rogers, and Jason Schweinsberg. So a slight adaptation of that model. So change the death chain and add in the feature that at a constant rate, each block will break. So blocks are merging. You see here at the constant rate C, any two are merging at constant rate C. So a merger will occur at rate C times I choose 2 if there are I blocks in the system. But then we're going to split each block at rate lambda, so total rate lambda I if there are I blocks in the system. And we're going to smash them into an infinite number of pieces. So we're going to send the system up to its boundary point plus infinity. And so the question one might ask is, can one come down from infinity? Is infinity a point that we can include in the state space and expect a sensible process? So the right way of asking that is, do we get a recurrent process when we include the boundary point plus infinity here? And actually the answer in this case turns out to be that we have a parameter regime here. So if we set 2 lambda over c to be theta, then we can get recurrence from theta between 0 and 1. And the process will actually enter repeatedly from plus infinity in the sense that we get an excursion process going on from plus infinity. So there's no first, if you like, incursion from plus infinity, but there's an excursion that we can build and then place that end to end through an etosynthesis, and we get a stochastic process where infinity is recurrent. And otherwise, if theta is bigger than 1, then we get theta as an absorbing state. Okay, one more example. So here's an SDE. This is the classical branching continuous state, diffusive continuous state branching process. And then there's an adjustment term here. This is, I believe, what Amari Lambert considered. This is kind of like coalescence here. One can think of a competitive term here going on, and entrance occurs at plus infinity for this model. But then more generally, if we go to continuous state branching processes in their full generality, this is work that Beresticki, Fittipaldi, and Fombona have done. So here is the SDE that you would normally write down. So all that, I'm not really covering it up properly, but this bit here is the main SDE for continuous state branching process, and there's the competitive term that they considered. And there is a question, well, this is now jumping, this one isn't, so in a sense this fits Feller's original situation. This one isn't, can we still talk about coming down from infinity? So I want to address the setting of what would be called a jump diffusion these days, and ask the question of, can we come down from infinity for this process? But I'm going to ask the question with a slightly different notion of infinity. So here's my stable jump diffusion. So here, X is a stable process. It's exactly the same as Feller considered, except I replaced the Brownian motion with a stable process. They are one-dimensional stable process. Sigma is going to be continuous and bounded away from the origin. So for those of you familiar with stochastic calculus of jump processes, I have to take the left limit here of ZT for the sake of provisibility. Okay, so I'm in. Can this enter plus infinity? can it enter from minus infinity? And actually now, because of jumps, can it enter from the 1-point compactification of the real line, which is plus minus infinity, so the union of the two infinities, if you like. Now, before, this wasn't considered for the setting of Feller, because if you imagine this to be a continuous path, there's no way we can think about starting at plus and minus infinity, because we need somehow to oscillate infinitely often at arbitrarily small times, which means I would have to continuously pass through any neighborhood of the origin, and that would slow the SDE down. There wouldn't be enough time to get back and forward coming in from plus and minus infinity. But now we've got jumps, that might happen. Okay, so let me be clear about what I mean about a stable process, because different people understand different things. So this is a rather full slide. So a stable process, I mean a Markov self-similar Markov process, a Markov self-similar Markov process, which is also a Levy process in one dimension, of course, always one dimension. And it has a scaling property being a self-similar Markov process. So if I multiply the process by a constant here, and I scale in time as such there, with c to the minus alpha, and alpha is going to be a special parameter, then when I start the process from x, what I'm looking at is equal in law to itself again, albeit if this one started at x, then this that it's equal in law to starts at c times x. Alpha is the index of self-similarity, and necessarily if this is going to be a Levy process, then the index has to be between 0 and 2. You'll immediately start complaining about this bracket here. It should be a closed bracket, but I want to exclude the parameter alpha is 2, because as you all know, that's Brownian motion. That's been done, so we're throwing that out the window for now. Okay, now as a Levy process, we describe its evolution, its semigroup, essentially by its passage from time 0 to time 1, from 0 to wherever it gets to in time 1. So we look at the Fourier transform. This gives us an exponent, psi z, and psi z is characterized in the special case. You may recognize this formula. This is the Levy-Hindchin exponent for a stable process. Actually, most of you will recognize this part of the formula here. I'm sorry, I'm not able to blue that out at the moment. Recognize this bit, but I've written this in a slightly different way to the usual way. So there's usually an alpha and beta parameter, alpha being the index here and beta being the symmetry parameter. But actually I've rewritten it in this format where rho is the positivity parameter. And that's just for more presentational convenience. Now, as most of you know, associated to every Levy process is its jump measure. So here it is absolutely continuous with respect to the Lebesgue measure. And the parameter rho here appears, and anytime you see a hat, by the way, hat means we're talking about whatever that value is, but for the negative of the stable process. So if you like, in the Levy terms, the dual of the Levy process. So here we've got a rate at which we're seeing positive jumps of size x. So when x is teeny tiny, we're getting an arbitrarily large rate of arrival. And this is the rate at which we see jumps which are negative and of size x. So sorry, it's proportional to 1 over mod x to the 1 plus alpha, and this is the constant here. So rho is the coefficient which kind of deals with the symmetry going on here. Some of you know the setting that a stable process is a subordinator, so that would be the case that we switch off entirely the negative jumps here. I'm sorry, I told my children not to be noisy during this hour, and exactly this is what they're doing now. So And here, if I take rho I can take rho to be 1 and alpha to be between 0 and 1, that would switch off this here. That would make this into the only contribution in the Levy measure. You'd have your increasing Levy subordinator. Some of you know a stable process to be in the symmetric sense, so that would mean rho is a half. And if alpha is 1, you've got back to your Cauchy process. Sorry, that keeps flipping. Okay, so I don't want to dwell too much on that, but for those of you who are familiar with stable processes, I mean the full class of stable processes. But I'm actually mostly going to focus in this talk on the setting that rho is between 0 and 1, so I get a contribution in both positive and negative jumps. Okay, so the first issue I need to address is whether the SDE makes sense. So when alpha is between 0 and 1, we need to be a little bit careful. When alpha is between 1 and 2, we're pretty much good. So when alpha is between 0 and 1, we need to take care of this explosion time here. Oops, that's not going down too well. This explosion time here. So the solution, I can identify the solution to this SDE in the weak sense as simply a time change of the stable process. And the time change here is the inverse of this clock. And this clock here is built from the sigma in the SDE. And if this total integral is finite, then we've got a problem. Then we get an explosion in the time change. And so, there it goes again, sorry. And so if alpha is between 1 and 2, this doesn't explode. And that's basically because x is recurrent, it visits the origin infinitely often. And so it keeps this integral growing and growing and growing. And if alpha is between 0 and 1, then we have a transience, and the process can kind of drift out to the outer regions of space. It kind of evacuates all compact domains containing the origin, and then this thing will become finite and we get an explosion. So sometimes I'm going to talk about the SD up to explosion, but actually I'm not sure I'm going to mention that again, because I'm going to work probably in this environment only in the near future, alpha between 1 and 2. Okay, so what do I mean by an SDE entering at plus minus infinity or plus infinity or minus infinity for this setting here? So what I mean is that the point, so let's take plus minus infinity. The point plus minus infinity is not accessible. If I take the semi-group that is induced by the law of the SDE, it's a Markov process, then I can extend semi-group onto the completion of the real line by plus minus infinity. And so I can talk about, you see here these px's, so I can talk about p plus minus infinity as part of the Feller extension. So I have also the Feller property holding on the complete domain here. And I need also this property that the process, which is written here as y for now, the process as t tends to 0, its modulus blows up, and its lim sup blows up to plus infinity, and its lim inf blows down to minus infinity. So it means as I look back in time towards the origin, I see the process exploring larger and larger distances away from the origin, both in the plus and the minus direction. And now once you've seen that definition for plus minus infinity, you can pretty much imagine how to adjust it for plus infinity or minus infinity. As I said, I'm going to talk about this case here, plus minus infinity. I'm going to restrict myself to alpha between 1 and 2 as well. But here's the full result that we have for this SDE. So these are all the possible values of alpha here. Here's the Feller case at the very end. This column tells me whether I have only positive jumps or negative jumps or both jumps, up and down. And so we see here that there's no, for alpha between 0 and 1, there's nothing doing. I cannot enter from plus infinity. I cannot enter from minus infinity. I cannot enter from plus minus infinity. Once alpha is 1 or greater than 1, then we start to see some action. So we can enter at plus minus infinity if and only if we have an integral test. Here it is up here at the top. Okay, so we get this log term. So it's a bit like Feller's, except we get this log term, and that's special to the case alpha is 1. Otherwise, when we look at alpha between 1 and 2, then we can come in from plus infinity only if we have positive jumps, and if and only if then we get this criteria holding. So this integral test is up here at the top. And this integral test is much closer to the Feller test. So you can see that if alpha is 2, it is the Feller test. And then, of course, similar behavior when we enter from minus infinity, except we need now only negative jumps. And if we want to enter from plus minus infinity, that can only happen when we have plus and minus jumps. And in that case, the integral test, I should say, you should take notes here of the R plus and the R minus here and the R. So that's telling you where the integral test is happening. So if we want to enter from plus infinity, we need to have the integral test holding over the positive half line. If we want to enter from plus minus infinity, we need the integral test to be over full real line here. Okay, and that's Feller's result down there at the bottom. Okay, how do I move on? There we go. So I think I've gone too far here. I'm going to start. I'm going to give you some background. I'm going to give you a sketch proof of this, but I want to give you some background to this first. I want to introduce you to this lovely Polish result of Krzysztof and Tomasz Stack. This is to do with space-time transformations of stable processes, and it goes as follows. So suppose you have your stable process. Again, I'm going to insist on two-sided jumps. Actually, I don't care what my alpha is for now. And I've got another clock here. So this clock, eta, is the inverse of this integral time here. So we're building up time depending on where the stable process has been, and then we take the inverse of that. So if I take 1 over the stable process, so I invert the path, if you like, this is an inversion through the unit interval -1, 1, and then I time change, then what I'm looking at is not a stable process again, but something that's nearly the stable process again. So first of all, I'm going to look at this not under P, but under P hat. So remember, P hat was the law of -x. So if you like, what I could be saying here is just stick a minus sign in front of this, and this is going to be considered under Px. Okay, so what does that give me? It gives me a self-similar Markov process, and it's equal in law to something very closely related to the stable, which I'm calling X with probabilities P circle. And of course, if this guy starts under X, then the transformation starts at 1 over X. So what is this? So it is actually the stable process, but under a dupe H transform. And the H transform is proportional to this harmonic function mod Z to the alpha -1. This mess in front of it is almost a constant. It's just a constant that changes according to whether Z is positive or negative. Okay, so if we took a symmetric process, then h of z would indeed be mod z to the alpha minus 1. So what we're saying, again, just to rehearse this, so I'm saying I take the stable process, I invert it, I negate it, I time change it. So I've made a space-time path transformation, and it's equal in law to the stable process, again, except dupe H transformed by this rather, almost rather pretty harmonic function. Okay, so question is, what is this process here? What is this P circle? What does it mean? What is it in relation to the original stable process? So it's a dupe H transform of it, but what does that mean? Well, it turns out I can relate the P circle to the original stable process via this form of conditioning here. So luckily, all the ducks were in the row already for us. So there was some work of Chamont and Panti and Rivero, and Kuznetsov, Pardo, and Watson. That might be me actually. And this looks at conditioning the stable process. So in this case, to avoid the origin. So when alpha is between 1 and 2, you can have a look at this and think, well, what happens when x tends to infinity? When x tends to infinity, we reward paths. Sorry, when x tends to infinity, and when x tends to 0, we punish paths in the dupe H transform. So not surprisingly, this P circle process corresponds to conditioning the process to avoid the origin in this sense here. So T0 is the first hitting time of the origin, and this is a notion of conditioning the process to stay away from the origin in the long time. Here F is an event up to time t, and here I'm saying keep it away from the origin at time t plus s, and then take s to infinity. It's rather a classical way of doing it. In the setting that alpha is less than 1, if we go back here, we see that we punish paths which go far away from the origin, and we reward paths that go close to the origin. And so it turns out actually that this would correspond not to conditioning to avoid the origin, but it corresponds to approaching the origin continuously by oscillating around the origin closer and closer and closer, and then eventually hitting it. However, I think I've only described this because we're again sticking to this setting of alpha between 1 and 2. Again, I'm sorry about the oscillation in the slides. Let's skip this bullet point here. That's for specialists. Now, what is in that slide, the executive summary of the last bullet point there, is that this process here, we can make sense of it actually starting from the origin. So it's a process which avoids the origin. So it's a stable process conditioned to never visit the origin, to stay away from the origin. But we can start the process from the origin. So actually, this statement I'm making here, which is that the law of the process started from Y converges in the weak sense with respect to the Skorohod topology to a process starting from the origin. This, in a sense, is another example of the kind of Feller-type entrance law we're interested in. And in fact, you'll quickly realize that I'm sweeping the entire problem of entering from plus minus infinity under the carpet by just telling you this bullet point is true, that I can condition from and actually that's the whole basis of proof. I use this to my advantage. I'm going to start with this circle process and start with this stable process conditioned to avoid the origin, And now I'm going to Dirac transform and through the SDE representation, and I'm going to make sure that all that behaves itself, and I can then map this entrance at 0 to entrance at plus minus infinity. And the integral test that you see in the theorem is what's going to allow me to control that proof, if you like, or control that logic. Okay, so I'm going to run that through with you. So my first step now is to kind of take the Bogdan-Zach transform and look at it again in the context of this SDE. So you remember that this SDE has a weak solution, and the weak solution is a time change of the stable process. But you also remember that the Bogdan-Zach transform says do a space-time change of the stable process, and you get to this conditioned stable process. So if I mash those things together, we get the following. Whoops. So here we go. So here's a function beta. So it's something like the time change function that appears above, except I've got 1 over x in it. And then I've got the time change function that appeared in the Bogdan-Zach transform. So now I'm going to kind of say things in reverse here. So I'm going to take the law of the stable process, conditioned to avoid the origin. I've put a hat on it. So what I really mean is I'm going to take the negative of the stable process, which is just a stable process with the roles of rho and rho hat interchanged, the symmetry interchanged, if you like. So I'm going to take x hat circle, so the negative of the stable process conditioned to stay positive. I'm going to invert it. I'm going to whack it through a time change. So here's the time change. The time change is based upon this beta clock here with beta up there that we just talked about. And what comes out of that transformation is Z. Don't worry about the dagger for now. The Z is equal in law to the weak solution of the SDE. And if I start x circle hat starting from 1 over x, then the Z process will start from x. Okay, so what I've done is I represented my weak solution to the SDE as an inverse 1 over of the negative of a stable process conditioned to stay positive. Now, let me just tell you about the dagger. The dagger is there because the transformation here will only tell me about the SDE until it first hits the origin. And it will hit the origin because x can hit the origin, and the time change is such that I can reach the time that x will allow me to hit the origin through here. Okay, so that's why I put the dagger on there. But more or less, that doesn't matter because I'm only interested in trying to get this process, Z, to start from plus minus infinity. Okay, so you can already see from this representation that starting this Z solution of the SDE from plus minus infinity is an issue of starting this x hat circle process from 0. And this is coming back to my comment that I kind of cheated here by just telling you, well, this is a process condition to stay positive, to stay away from the origin, and you should trust me. I can also start it from 0. So that's me sweeping the whole thing under the carpet. But I'm going to use it here. Okay, so let's run through heuristically the proof that this integral test, which appeared in the theorem, implies that plus minus infinity is an entrance point for this SDE, or the solution, the weak solution to this SDE. Okay, so as we've said on the previous slide, so Z is equal in law to time changed x. That's this bullet point here. It's rather difficult sometimes to blue things out. I'm so sorry, I'm a bit chaotic. So Z is equal in law to time changed x. And so if x is entering at plus minus infinity, then if Z is entering at plus minus infinity, then 1 over Z, or indeed 1 over Z dagger, I don't really care about hitting the origin later, is entering at 0, but it's crossing the origin infinitely often for arbitrarily small times. That's an important feature of this bullet point to this bullet point. Entering at plus minus infinity means I'm going to have to cross infinitely often the origin. And so when I invert it, it is going to cross the origin infinitely often still. Okay, so according to my previous theorem, so if 1 over z dagger is entering at 0 and crossing the origin infinitely often, then I want this x circle hat, so the negative of the stable process, conditioned to avoid the origin with a time change of this theta. This guy needs to enter at 0, crossing the origin infinitely often for arbitrarily small times. Okay, and that's from this previous result just here that we spoke about. I remember theta is with the beta transform. Now, that should happen because I told you a stable process conditioned to avoid the origin can enter at 0. However, we mustn't forget about the time change. So it can enter at 0, providing I can control the time change. And so to control the time change, if we whiz back again to this slide, so the time changes by this theta here. The theta is the inverse of this integral clock here, which is based on this beta function here. So I need to control this integral in essence as the stable process condition to avoid the origin, or the hat stable process condition to avoid the origin, tends to 0. So I need to make sure this thing doesn't blow up. It doesn't do anything stupid. And so as I drag here the starting point of x hat circle to 0, the theta time change behaves itself as well. Of course, I'm glossing over a lot of detail here, but this is just the rough outline of it. So to control this integral, it's enough to control its expectation as x tends to 0. Okay, so don't forget it's beta of the stable hat process conditioned to avoid the origin. Controlling that, it's enough to control the total integral here up to infinity. And then take the limit as the starting point tends to 0. Okay, well, here I've got some notation at the bottom. So I'm using this term here for a resolvent of a Markov process y. So any Markov process y has resolvent gx dy. So back up here, I want to control this guy here. So how do I do that? Well, I'm going to first write it out in terms of its resolvent. So there's the beta function appearing here. This is the resolvent of the negative stable condition to avoid the origin. Now, luckily, a nice little trick is the resolvent of the condition process, being a Dupage transform, is the resolvent of the process killed on hitting the origin with the h function that we defined earlier that was more or less mod z to the alpha minus 1. And so there it is. I've filled it in. I've forgotten about constants. I've thrown all the constants away. I don't care about constants. That's not going to affect the integral. And this resolvent here, I thought this would be in the literature. So I went hunting. So I want the resolvent of the negative of a stable process. That's a stable process again. The resolvent of a stable process killed on hitting the origin. Well, I couldn't find it. So I had to prove it myself, and here it is. It's a rather nice, cute formula here between this bracket and this bracket here. And then, of course, as I take x to 0, lots of convenient things happen. Well, I have a little bit of a problem down there, but if you're prepared to trust me, the whole thing is controllable, and essentially, if this integral is finite, then you can make sense of this limit here, this guy here. Okay, which is exactly controlling this expectation, which is exactly controlling the weak convergence of this functional, which is exactly controlling the time change, which is exactly controlling this guy being able to enter at 0, which is exactly controlling 1 over the solution of this SDE entering at plus minus infinity. Okay, so I've done one direction, I've done a sufficient direction. What about necessity of that integral test? Now this is the dodgy direction. So this is the direction where I'm going to give you a scratch proof, but it's a terrible scratch proof because it's all lies, but it captures the essence of what is really going on for the rigorous proof. So we're going to start with this proposition, which is based around Hunt-Nagasawa duality. So Hunt-Nagasawa duality is about taking a Markov process and time reversing it. So in particular, the paper of Nagasawa in the late 60s gives us nice criteria that we can check. So if I take a forward-moving Markov process and I have a suspicion that if I time reverse it, and even that needs a careful definition, if I time reverse it, I'm seeing another Markov process. The Nagasawa paper gives me nice criteria to verify whether my suspicions are true or not. Okay, so here is a proposition which is essentially verifying what I think is the time reversal of a relevant Markov process that appears in our setting. So I'm going to start, as always, with this core object, which is the stable process condition to avoid the origin, or the negative of a stable process condition to avoid the origin. And I'm going to time change it. And I'm going to time change it, call the time change z hat circle. And the time change is, at the moment, it's an arbitrarily chosen time change. So this iota t is a little bit arbitrary. So there's no apparent reason for it at the moment. However, what I'm saying is, if plus minus infinity is an entrance point for the solution to the SDE, then I'm quite within my rights to pick a last exit time. This k is going to be a last exit time. And I can time reverse the process from that last exit time, any last exit time. And here I've just got a little minus sign because I need to make paths CAD lag again. Going forward, I have CAD lag when I reverse them. They're not CAD lag anymore, but if I put a little minus sign, that deals with that. Okay, so if I time reverse my solution to my SDE, okay, killed and hit until hitting the origin, up to some last exit time, like the time when I first hit the origin. And I do that with z starting from plus minus infinity. Then what I'm looking at is another continuous time Markov process. And that continuous time Markov process agrees with the one that I have built here with this unusual choice of time change here, or this at the time of introducing it, this arbitrary choice of time change. Okay, so this is simply a verification using Nagasawa's duality criteria. In fact, Nagasawa wants us to check that my two assumed dual processes, so that would be Z dagger and then this process here, so Z killed on hitting the origin, and this one here, they need to fulfill some kind of detailed balance equations, if you like, if you want to call it that, with a reference measure. And the reference measure is a little bit complicated. It's built up from the starting measure of Z circle hat and its resolvent, which actually turns out to be this rather cute measure here. Okay, so keep that in mind. So what I'm saying is, if I time reverse the process entering at plus minus infinity from a last exit time, for example, the time it first hits the origin is a last exit time, or I can treat it as a last exit time. Then when I time reverse, I see a process which explodes to plus minus infinity. And the two are time reversals. One is time reversal of the other. Okay, now here's the dodgy bit. And I know that we have got some people in the audience who are grandmasters in this particular arena. So I'm going to make my apologies immediately for the carelessness with which I'm stating this. So if I want to understand a necessary condition, integral condition, for this process to enter at plus minus infinity, if I want to show that entering this at plus minus infinity necessarily implies that this integral test holds here, then what I can do is I can kind of think of this one point addition as a compactification of the space, and then I look at Guittor's. Guittor wrote this nice paper in the 80s saying, well, look, everybody's got their definition of transient, so basically they're all equivalent. So on the one hand, some people define it as last exit from a compact set being almost surely finite for any starting point. And on the other hand, some people see it as saying the resolvent on any compact domain is finite. Well, so if this thing is starting at plus minus infinity, or better said, if Z dagger, the process when it first hits the origin, starts at plus minus infinity, and it enters, no problem, it's Feller, it works its way all the way down to absorption at 0, then that sounds pretty transient to me, okay? And in fact, because this space is compact itself, we could say, well, that must mean that the resolvent of the SDE is, well, I should have a dagger here, the SDE killed on hitting the origin is finite over the whole domain because the whole domain is compact. But on the other hand, this Hunt-Nagasawa duality says, well, my occupation of the whole domain, again, apologies, there should be a dagger here. My occupation of the whole domain until first hitting the origin when entering at plus minus infinity. Well, if I time reverse that and I look what's going on in the reverse, well, I've hit the origin. So I start at the origin and then I blow up to plus minus infinity. So my occupation moving forward in time, starting from plus minus infinity, must be my occupation moving backwards in time, starting from 0. Now that's a really dirty version of the truth. So apologies, it needs a little bit more rigor than what I'm saying, but that's the crux of it. And so if I look at this thing being finite, so this needs to be finite because it's equal to this. And if we're saying this enters and then can hit the origin from plus minus infinity, this must be finite by the criteria of transience on a compact space. And so I just verify what this object is. It is, remember, it's a time change of a Dubh transform of the stable process hitting the origin. So here's the resolvent of the process hitting the origin. Here's the Dubh transform, and here is the time change happening. And again, if you're willing to trust me, a little bit of fiddling around, I actually need this X to be 0. I haven't set it to be 0 because you're going to have a problem down here already. But a little bit of trust, this thing can be sorted out to look like or to be necessarily forcing this integral to be finite. Okay, so essentially entering at plus minus infinity of this SDE, because it's the time change in law of a stable process, and because of this Riesz-Bogdan-Zach mapping the origin to plus minus infinity, and because of time reversal, we can get the main result that we had all the way back down here, this red one here. So alpha is between 1 and 2. And we're looking at up and down jumps. Okay, if and only if this integral test over the real line is finite. Okay, Life has come online, which means he wants me to shut up. I've only got a couple more slides, Life, if you'll indulge me, and they take virtually no time at all. So I've done two-sided jumps. I'm going to skip that. But I want to say you can, if you think about the reversal, then the reversal is converting entrance into explosion. So actually we could redo our analysis and look at what do we need for explosion to occur in that SDE. If you remember right at the beginning, we have to be a bit careful about that when alpha is less than 1. And not surprisingly, we get a table here where I get criteria, if and only if necessary and sufficient conditions for explosion, with down jumps, up, down jumps, explosion to infinity, explosion to minus infinity, explosion to plus minus infinity. All the actions happening exactly where we didn't get any action for the entrance from plus minus infinity, and that's with alpha between 0 and 1. Thank you very much.
Hey, thank you, Andreas. Unfortunately, now you ran over time and we cannot try our game with hands up. Oh, perhaps one
but
question.
You stole some time from me at the beginning.
Well, let's try it once with Robert along. So now you should.
Hello, I don't know if you can hear me.
Yes.
Yes, I can, yeah.
Okay, well, thank you very much, both for the beautiful lecture and for organizing this. My question is actually more a comment than a question. During your lecture, I apologize for practicing what most of us usually do during a lecture anyway, which is work on other things. And that actually worked quite well. So thank you very much and congratulations.
Thank you.
Okay, we do one more. Milton, you should be unmuted.
Okay.
And so you should.
Okay. Can you hear me?
Yes.
Okay, great. Of course, first, thank you. I want to thank you, both of you, for this very nice initiative. I took my chances to make this program mandatory for students at Impact, which are currently back at their homes. And so you will have some extra audience guaranteed for next week's. But okay, the question is that so when you have diffusions and you know that the boundaries are entrance or regular, etc., I know how to set up nice boundary conditions for the generators.
Yeah.
So can you do the same thing in this case? I mean, to set up the nice boundary conditions for the generators of these diffusions, jump diffusions.
Yeah, so in principle, I would say, so of course the generator of a stable process can be a little bit of a nasty beast. It's an integral differential, well, it's an integral operator, a Gaussian component. So if you are strong enough on the analysis, I would say yes. Ultimately, it should be doable, but I'm not convinced that the literature is mature enough in that aspect. Problem at the moment. So the understanding of the problem offending half of the people in the seminar here. It's probably more that this is my way of dealing with things. I was particularly interested in the representation of the solution with life through time changes. Somebody might come back and say, yes, this can be done analytically through the generator. I'm a little bit suspicious that that's not doable. I didn't feel the literature was mature enough for that yet. And that is because of the nature of the generator being rather nasty.
Okay, thank you. Thank you again, Andreas. Now we need to try to change the setup to Nathaniel.